Good morning, and thank you for joining us this morning for another Concrete Ontario webinar. Today's topic is the 2019 edition of CSA A23.1, A23.2. We here at Concrete Ontario have been patiently waiting for the release of this document for a while now, and as it impacts many of the different initiatives we're actually going to be looking after. So we are quite excited for today's presentation. My name is Alan Carey. I'm the Director of Technical Services at Concrete Ontario, and I will be your facilitator this morning. Just before we get started, as always, just a couple housekeeping items. For new attendees who are not familiar with how we actually run the webinar, this will be approximately a 35 to 40-minute webinar, and we will leave time at the end for questions. All participants are currently muted and will remain that way for the duration of the webinar. If you do have any questions, please use your GoToWebinar questions pane on the right side of your screen and type in your questions. We will leave all the questions till the end. This webinar will be recorded and will be posted on the Concrete Ontario YouTube channel. And to make access easier for everyone, we will be sending a link to the YouTube channel video, as well as a PDF copy of the presentation. That was one of the questions that already came up this morning. Now, in terms of the document itself, it's about 882 pages, approximately an additional 200 pages compared to the 2014 edition. It is available on the CSA website for approximately $242. And we would like to encourage everyone to purchase a copy if you are in the concrete industry. It's a very important document that we reference daily. And also to make sure that you are complying with the latest requirements that are in this new edition. Now, how does this actually impact the association? It impacts our plant and truck certification program. Obviously, we want to make sure that we are complying with the latest requirements of the CSA standards. And we will be updating our audit checklist in the coming few weeks to make sure all the requirements are reflected in that document. We will also be updating our publications. Most of you are familiar with our Power of Concrete documents that are on our website. Most of we have updated several of them, and that will be available in the coming weeks. I'll talk a little bit about that at the end of the webinar. In terms of what does CSA 2019 have to do with the municipal specifications, we do represent, we have representatives on the OPSS structures and pavement committees. And we are ensuring that the 2019 edition is being referenced in all upcoming standards. A good example is OPSS 351 and 353, which is your sidewalk and curb specs. They will be released in November, and they already are referencing CSA 2019. This new standard will also impact the field testing course, the CSA base course that we run through ACI International and ACI Ontario chapter. There are some significant changes to the volumetric method and the density testing method. So we will be updating our workbook, our presentations, and ACI International is currently looking at updating the exam as well. That should be ready to go for the January course in London, the 2-day course that we are offering. And the last way that the new edition of CSA is impacting the association is we are in discussion with the MTO to ensure that they are going to be adopting the CSA exposure classes as well. We have started that discussion, and it's very important that we align the entire province to conform to the latest CSA A23.1 standards. Having said all that, I will be introducing your presenter. Your presenter today is world-renowned concrete expert, Dr. Doug Hooton. Most of you know Doug. He's a phenomenal guy, and we are very, very lucky to have him today to provide an overview about the new standards. Now, Doug is off to China in the next couple of days, so we're able to lock this in just in time so we can provide this update to you guys today. A little bit about, you guys know him, but just to give everybody else a sense of who Doug is and what he actually does in the industry, which is a lot. So Doug is a professor and NSERC Cement Association of Canada Senior Industrial Research Chair in Concrete Durability and Sustainability in the Department of Civil Engineering at the University of Toronto, where he has taught for more than 30 years, and that includes myself. His research is focused on the fundamentals of durability, performance, and cementitious materials in concrete, as well as on performance tests and specifications for concrete. He has been actively involved with developing and calibrating tests for AAR, chlorine ingress, sulfate attack, freeze thaw, and de-icer salt scaling to long-term exposure sites and field performance. He has also worked in the development of performance standards for concrete as well as for novel cementing materials. He is a fellow of the Canadian Academy of Engineering, the Engineering Institute of Canada, and the Institute of Concrete Technology in the UK. He's a fellow of Ryland, chairs their Educational Activities Committee, and is a member of several of their technical committees. He is an honorary member of ACI, serves on the ACI Board of Directors, chairs ACI Committee C233 on slag cement, ACI C130A on sustainability of materials, and is secretary of ACI C201 on durability. In Canada, he is the past chair of the CSA A23.1 Committee on Cementitious Materials, and is currently the chair of CSA A23.1. So there's no better person to present the update on CSA 2019 than Doug. And I just want to welcome Doug to the presentation. Doug, are you there?
I am. Thanks, Alan.
Perfect. No problem at all. Having said all that, thank you very much for helping us out today. We really appreciate your help. And I'll turn it over to you now.
Okay, great. I will wait to show my screen. Okay, get up and running. So you can see my screen now?
Yes, you're good to go.
Okay, hopefully everybody can see it. Well, good morning, everyone. Hopefully you can stay awake for this exciting presentation on the new A23.1 and 23.2 standards. So the English version of the standard was published in late June. As Alan said, we were waiting for it. So it has a number of revisions. The French edition, they've had some issues with it because of the translation problems. It probably won't be out till September in French. And of course, because it's the 19, we sequence these things. So the cement standard came out in 2018, the A3000. So it's referenced in the 2019. Now that the A23.1 is out, we had to meet the deadline to be referenced in the next version of the National Building Code. And then once the National Building Code adopts it in 2020, the Ontario and other codes will pick up on it. The provincial codes will pick up on it as well. So there's a sequence to the way the CSA standards are organized, so we feed into the building codes. And just to mention the cement standard, which came out last year, one item of possible interest is that we're looking at different supplementary cementitious materials. We have fly ashes, slag, silica fume, and some natural pozzolans, but one that's been introduced is ground glass, municipal ground glass that's been collected and crushed. It's not covered in the A23.119 yet, but it probably will be in an amendment. And because of all the recycling of glass, ground glass as a pozzolan is occurring both in the US and Canada. I think there's 5 companies in the US and at least 2 companies in Canada. I think Quebec and New Brunswick have companies creating ground glass to use as a pozzolan, because it's glassy silica, which is essentially what SEMs are. And so I thought I'd spend 2 slides on that just to explain it, because it's not an A23.1 yet, but you may see it at some point. So anyway, it's just clean glass that's been ground up to the cement fineness. And there's 2 types of glass. The bottle glass is high alkali glass, so we call that G sub H. And if it's from fiberglass recycling, it has a lower alkali, so they call it G sub L. But I don't think there's anybody doing the fiberglass one in Canada. So it's container glass, plate glass are the main components here. And they're very consistent in quality. Container glasses are almost all identical in composition. And it works as a very effective supplementary cementitious material when it's ground up. But the main concern with it is the high alkali content. It's up to 13%, maybe even higher sodium equivalent alkali. That way, if you had an ASR problem, you wouldn't want to necessarily use this material as an SEM. But you can control it if you put enough regular fly ash and slag together with it. And that sort of work's ongoing, and I think that's what we're looking at before we adopt it in the concrete standard. Now, ASR is not a big deal in the Greater Toronto area, but much of Ontario has alkali silica reactive aggregates, so it would be a concern. Okay, on to A23. So the way the standards committee works, we had 38 voting members and 31 associate members that represent different parts of the industry. We have producer members, which would be the concrete producers, raw materials suppliers, which would be the aggregate and cement and admixture suppliers, service professionals, which are the consultants, testing agencies, users, which would be people like MTO and that, general interest, which would be somebody like me who's just an academic or has no stake directly in industry, and then regulatory interest members, which we don't have any, I don't think, on the committee. The committee up till the new edition came out was chaired by Chris Rogers, formerly with the MTO, was their geologist petrographer, and I've just taken over since our last meeting in May. And the executive committee of the new committee that will come out with the next edition in 2024, Bart Canters from the Concrete Ontario is on the executive, along with Phil Trunk, formerly of CRH, Mike Thomas from University of Brunswick, and Gordon Lehman from not Stantec. Where are they, Stantec? Out in Dartmouth, Nova Scotia. Anyway, the organization is, we have it organized in chapters. So the chapters of the document, because it's a big document, as Alan said, is 800 and something pages. A lot of that is in A23.2, which is the test methods, but A23.1 is still 150 pages or so. So we have any reference publications that are up at the front. We define the materials, definitions. Then chapter 4 is concrete and materials properties. And we have production and delivery is 5. 6 is formwork reinforcement and pre-stressing considerations. 7 is placing, forming, and curing. 8 is concrete with special performance or materials requirements. So all the different specialty materials are in there, as opposed to the regular ready mix. And I'll walk through a couple of those. And then chapter 9 is on the residential housing and small buildings, the R class. So section 8, as I mentioned, all the specialty ones. 8, we have high performance concrete, which has been there, but we've added a new section of ultra high performance concrete, since that's making it has been made its appearance in Ontario in the last 5 or 6 years. And we have a new annex that goes into ultra high performance concrete. It's almost like a specification, but it's non-mandatory. It's an annex. The other ones are pretty much the same. We have pretty much the same. And I think the shotcrete's fairly new as well. It's been added to the section on shotcrete. Okay. So I'll walk through the major changes, then I'll go into more detail. One of the biggest changes is in clause 4. And we've taken a bunch of the stuff out of clause 4, which people were concerned that some of that stuff was contractual information. It shouldn't be in the body of the standard. So separating out the requirements for the concrete from the contractual stuff, we put the contractual related information into standard practices, which are directly referenced in clause 4. So we have 130A for sampling, testing, and inspection of aggregate products for use in concrete. So it's the aggregates one. Then the 2 for concrete are 24C and 25C, and one of them is for sampling, testing, inspection of concrete for qualification purposes, 24C. And then sampling, testing, inspection for acceptance purposes is 25C. So separating out the qualification requirements from the acceptance requirements. We've also made substantial changes to the section on mass concrete, including the requirements to submit a thermal control plan for controlling and monitoring temperature and temperature gradients. I mean, a lot of the big contractors are doing this already. So it's a matter of trying to bring up to speed to avoid some of the problems that have been going on with thermal cracking. Because mass concrete isn't necessarily things bigger than a meter anymore with high cement contents, and there's substantial heat in even smaller elements now. We got new requirements for slump of concrete for interior concrete floors, updated Annex P on potential deleterious impact of sulphide minerals in concrete aggregates, including some new test protocols related to that. And this has to do with a big problem that happened in Trois-Rivières in Quebec over the last 5 or 10 years, where huge durability problems, and I'll talk more about that later. So there's some new requirements for testing aggregates, which will impact on aggregate suppliers across Canada, and I'll talk about that. And I said there's a new annex on mass concrete, and the new Annex U on ultra high performance concrete. We're talking about ultra high performance. We have two classes, minimum strengths of 120 and 150 megapascals. But some of these concretes are getting 250, 300 in some cases, but we've set these limits at 120 and 150. And we have one new test method, 26C, A23.1 26C, bulk electrical resistivity of concrete. And again, this is similar to the 23C, the rapid chloride permeability test, but it uses just measures electrical resistance, and you can, instead of spending the whole day measuring the Coulomb values, you can do this test in about 1 minute, and essentially gives you the same information. Okay. One other change, the only change to Table 2, which is the exposure class table, is this thing I've circled here to separate out whether concrete's going to be exposed to freezing or not. Because there were some concerns raised, especially with some of the higher strength levels, that it, like the CXL, where you need 50 MPa, that if you didn't have freezing thawing exposure, it was difficult in some cases to get 50 MPa or the required strengths with air. And there was no need for air because they were never going to see freezing and thawing in service. So the idea is just, we've added that new column to say if it's not exposed to freezing, the air content requirements are not applicable. That's what the N/A stands for. So it's just a clarification issue. There's been no other changes in the standard except to say, look, if you don't have freeze thaw, you don't need to supply air. Sort of a common sense approach, but it had to be outlined because some designers and that were not accepting it otherwise. Okay, well, this change was already in an amendment that came out last year in the A23, that Portland limestone cements, those cements that are have up to 15% interground limestone, are now allowed in sulfate exposures. Before, we had some special requirements for testing them if they're going to be placed in sulfate exposures. But based on extensive research that, well, I was involved in, and Mike Thomas and others were involved in, we've now removed all those requirements. And so now you just test it the way you would with any other cement. And there's no special limits on the concrete. And well, there it is there. So we've changed Table 3. We've added moderate sulfate limestone B for blended cements. That's what the MSLB, and then high sulfate limestone blended cement to the table categories for the S1, S2, and S3 categories, which are based on severity of exposure. And we've also added HSE, an equivalent, because some specifiers, especially in Alberta, were not allowing ready-mix companies to supply a GU cement plus, say, a slag or a fly ash as a equivalent to a blended cement. They said, well, it's not on the list. So we've created HSE as equivalent to a high sulfate resistant blended cement to say that if you make SEMs, you can use GU cement and call it a sulfate resistant equivalent. And it seems like common sense, but there were some designers, certainly in Alberta, that were not accepting this, which was causing problems. And so you can use those cements, and then you have, for anything that's not a straight Portland cement, there's performance requirements in terms of a mortar bar expansion test. That's always been there. So just since I'm on the sulfate story, Where are sulfate exposures? Of course, there's big problems in the prairie provinces. The lower parts of Alberta, Saskatchewan, and Manitoba are very high, ultra-high exposure sulfates. It's an old seabed. But there's also sulfates near Niagara and along Lake Erie because there's gypsum-bearing layers in the shales there. In the Toronto waterfront, south of Front Street, is a moderate sulfate exposure because, again, that same shale layers, which is now, it's basically landfill south of Front Street. Used to be the lakefront. And of course, there's problems in sewer pipes where we require sulfate-resistant concrete, although it's really an acid problem because of the bacterial acid formation. Sewage treatment plants, some industrial effluents, and seawater is considered a moderate exposure. In addition, of course, it's always chlorides because of the salt in seawater, but it's also a moderate sulfate exposure. So that's where the exposures are. And that just shows you where the exposures are in the prairie provinces. And of course, that extends down into the states, through the Dakotas, Colorado, and all that. They have some severe sulfate problems. And we're looking at high concentrations in some of these cases, which I've listed there. In Alberta, some of the soils, the Gardner Dam in Saskatchewan, they had severe sulfates in the soils there. But this is a map I was able to find with sulfate contents of well water in southwestern Ontario. Unfortunately, I don't have it for the rest of Ontario, but right along the escarpment line, you can see these big black circles. And those are the ones that are moderate, up to almost 3,000 ppm. Or milligrams per liter sulfates in the water. So there are sulfate soils right up through there. The ones with the little, anything less than 150 is considered not a sulfate, so any of the smaller dots are not a problem, but when you get the bigger dots, that's where there are sulfates. And that puts limitations on the concrete, of course. S3, which is the lower moderate category, is 0.5 max water binder ratio and 30 MPa. And S2 is 0.45 and 32 MPa. Okay. Well, I mentioned the sulfides and aggregates, this Trois-Rivières problem. And we had a note in the, which is shown there and underlined, that certain sulfide minerals, and people are aware of pyrites, iron sulfide that'll cause rust stains and that. But pyrrhotite was one that nobody had paid much attention to, but it's far more severe than pyrite, and it causes some durability problems, which I'll show you. And so there was serious problems, as I mentioned, around Trois-Rivières, Three Rivers for you non-French speakers. And the same problem is now outcropped, a very similar rock formation in Connecticut, just south of there. And that's caused some big legal issues. So we've developed some new standards. There's been a lot of research on this, especially by Benoit Fournier at Laval University and Medhat Shiada at Ryerson, to come up with some of these new test methods, which are located in Annex P of the standard. That's an example, a picture out of Annex P showing a foundation, the cracking in the foundation of a house that's only about 2 or 3 years old in Trois-Rivières. And it can happen with 1 or 2% of the sulfide sulfur in the aggregate. The Europeans have a limit of 0.1% sulfide sulfur if it's pyrrhotite. And they've had to raise over 100 houses. It came from one quarry near Trois-Rivières, and these are brand new homes. They basically had to raise them up, remove the foundations, and replace the foundations. And it's been making the news since 2013. People are looking for money from the government. Quebec's thrown money at it. The cost of moving one house or fixing one house was $125,000, all because somebody didn't test the aggregates. If they tested the aggregates and maybe there was more definitive information for testing, hopefully this would have been avoided. So it's relatively unique to Quebec at this point, but there's a potential for it to occur in other areas. So the new test requirements will be cross-Canada requirements for aggregate testing. This is a foundation in Connecticut, again showing the cracks. And some of these cracks are more than 1 centimeter wide. They're just opening up. So is pretty severe. So the test methods we've thrown in there is to look at sulfide sulfur content of aggregates, and if it's greater than 1%, the total sulfur in the you're supposed to reject the aggregate. If it's greater than 0.15% but less than 1, you need to do some of these testing. And if it's less than 0.15%, you can accept the aggregate without any testing. So it's going to require aggregate producers to measure the sulfur content of their aggregates. That's going to be a new requirement. And so that's the first test, test the sulfur. The second one is it's a funny name, oxygen consumption test, because sulfides are reduced minerals. So they all want to oxidize, which is what pyrite does and causes the rust. It oxidizes. And pyrrhotite oxidizes more severely. So they measure the amount of oxygen that you put in a sealed container, the aggregate, and measure the amount of oxygen that's consumed by the oxidation process. And if it's above a certain amount, then you do a mortar bar test. So test number 3 is a 90-day test with mortar bars with the crushed aggregate after some cycling in an oxidation fluid. Hypochlorite is just a way of oxidizing the sulfide minerals so that they expand. And you can see the cracking of a mortar bar there where they've had this problem. So it's a pretty severe set of tests, but again, it's to address this issue, which has cost huge money. In fact, the federal government has just put something like $4 million into a research program at Laval University to further work on this issue so it doesn't happen again. Okay. While I'm on aggregates, I just want to remind people that starting in 2014, A23.1 allows combined aggregate gradations, optimized combined aggregate gradations, in addition to the standard picking a fine aggregate and picking a coarse aggregate, often which leaves a gap and doesn't lead to optimum packing. You can actually optimize the whole gradation as a single fraction. And there are advantages doing that if you have enough bins at the plant to do that. Even 3 bins is sufficient. You can lower the cement content of the concrete, maybe up to 15%. And if you have less cement paste in the concrete, you're going to get less drying shrinkage. You're going to get lower permeability because permeability occurs through the paste fraction. So there's some economic advantages. There's also technical advantages to doing this. And it's in section 4, again, combined aggregate gradations. It's also an example given in Annex Q. And you basically optimize the whole gradation of the aggregate. And then for testing purposes, you split it on the, it's on the 5mm sieve, and you test everything above 5 as a coarse aggregate, everything minor than the portion that's -5 as the fine aggregate. So often this can be done just by fitting an intermediate material, even waste chip materials or intermediate material that fills that gap between the fine and coarse aggregates, so you get better packing of the aggregates. And again, you can get higher strengths, lower permeability, lower shrinkage, and better, more sustainable concrete because you're reducing the cement fraction and lowering the paste content. Anyway, yeah, there's the split, and you test according to the aggregate tables based on the plus or minus 5mm fraction of that, of the combined aggregate. So anyway, it's out there. I'm not sure how many people have tried it, but it offers an opportunity to reduce cement content in concrete and make better quality concrete. And there's some uniformity requirements to check that you're getting a uniform combined aggregate gradation based on, at the bottom there, that the sieve fractions don't change more than a certain amount over time. Okay, on to the 2019. Now, section 4.4 probably has the biggest impact on the producers here. So as I said, we've developed these new standard practices and taken a lot of the information out of 4.4 and put it in these standard practices, and 4.4 just references these practices. And again, to remove the contractual bits out of the body of the standard, which a number of agencies like the MTO had problems with. And as I said, we got the one for the practice 24C for qualification purposes of concrete, and 25C for acceptance purposes. And so 4.4 now says things like 4.4.1 and 2 says submittals shall be prepared and submitted in accordance with the requirements of Table 5, which is the performance versus prescription table, and A23.2.24C, which is the standard practice. So you go, for the submittal purposes, you go to the standard practice for things you need to put in the submittals. And submittal requirements shall be, this is out of into the standard practice now, 24C. The submittal requirements should be appropriate to the scope, size, and nature of the project. In other words, for small projects, you're not going to do as much as for a big project. And the supplier shall submit documentation to the satisfaction of the owner demonstrating the proposed mix design will achieve the required strength, durability, and performance requirements. That's all in the standard practice now. And unless otherwise specified, include a review of data demonstrating the potential performance of the proposed mix design, and if required in the contract documents, could require trial batches of a proposed mix design to get the test data. And the practice repeats what's in Table 5 for the performance alternative, what the supplier, concrete supplier, has to certify, which is right out of Table 5. Just saying that, certifying the plant, equipment, and materials comply with the requirements of the standard, certifying the mix design satisfies the standard, and production delivery meets the requirements of the standard, certify the concrete complies with the performance criteria specified, implementing a quality control plan to make sure the owner and contractor's requirements will be met, if required, and provide documentation that the supplier meets industry certification requirements, if specified. So that's right out of the existing Table 5. There's nothing new there, it's just put it right into that standard practice. So back in what's in 4.4, they've added material on the testing labs are responsible for lab and field personnel shall meet the requirements of A23 to the appropriate category, or the ISO 9001, and that's in because the Quebec people use 9001, Quebec industry. So the lab people have to be certified. All testing reports is distributed and available for audit by the certification. And all test data has to be reported within 5 days. I don't think that's changed, but that's the test lab responsibilities. And for acceptance purposes, as opposed to qualification, you go to 25C to do all the sampling and testing according to 25C. And then subject to project specs, the owner may accept or reject proposed materials and mixed designs based on information provided in the pre-qualification submittal. But that's a separate issue. Okay. So a lot of it, there's almost no change, just in 4.4 now, there's almost no changes in total, but a lot of the information's just been transferred to these standard practices. So there shouldn't be anything too much new there. We just tried to make almost no changes, just moving material, some sections where we thought it was contractual to these new practices. And on reporting test results, this is in clause 6 now. Test results should be provided to the owner, contractor, and concrete supplier within 5 working days of the test. Both lab and field reports shall include the information required by the test methods. And there's a sample test report for strength in the annex of A23.2. And if there's a dispute where there's more than one set of test results available from independent testing labs certified to the CSA, all test results shall be considered by the owner unless there's a defined referee testing program in place. Like I think MTO has a referee testing program. But so it requires people to consider all the test results. So if the concrete supplier has their own certified lab testing result, they can submit that data and it has to be considered. And the contractor responsibilities in terms of test specimens, the contractor has to provide and maintain for the sole use of the testing agency adequate facilities for safe storage and proper curing of concrete test specimens on the project site for the initial curing period, and that includes a protected and temperature controlled area to comply with the standard. In this case, they've used a large dog to provide the protection. I'm not sure about the curing. And so this is the mass concrete section in the new Annex T now. So fresh concrete, and it covers this annex: fresh concrete placing, maximum temperatures, maximum temperature differences, meaning from the center to near the surface, thermal control plans, including insulation and curing. So that's all covered in this new annex, a lot more information. And it's to deal with some of the problems like this. On the left, you've got a brand new subway station tunnel. The station hasn't even opened yet, and they're repairing cracks that are leaking because of thermal. There were thick walls, and they were restricted in their mix designs, and they couldn't avoid it with the mix designs they used. But hopefully, if they use this thermal control plan, they could avoid that. And the one on the right is a picture of an underside of an MTO bridge deck that was cracked right through the deck, right at the get-go before they waterproofed it, and the water's leaking through. And those are thermal cracks, transverse cracks in the deck. And this is an interesting graph. It's from a paper in one of the ACI special publications. Unfortunately, it's in US units, but I like it because it shows where you've got a concern. So the vertical bar shows anything greater than 1 meter to the right, less than a meter to the left. And that horizontal bar is 450 kgs of cementitious materials, and so higher at the lower end. So even when you have lower cementitious materials contents and less than a meter thick section, these red zones are severe areas of high risk of thermal cracking. So you could only be half a meter and still be on the edge of this if you have high cement contents. And of course, the green is good. Yellow is risky, but not as risky as red. But I think it helps put things in perspective because of the high cement contents and higher strengths that we're placing. Mass concrete isn't just big things anymore. And so thermal cracks are showing up in areas where we wouldn't have expected them 30 years ago. And it talks about how to do temperature monitoring, measuring the near surface temperatures between 25 and 75 millimeters from the surface, as well as interior of the concrete, and look for differentials. And the thermal control plan requires the contractor to submit to the owner a thermal control plan and how they're going to monitor this and make adjustments if they need to, with all this information required, including avoiding thermal shock. A lot of times winter concrete, when they remove the forms and it's really cold out, you're going from a hot concrete to like a minus temperature exposure, and it can cause thermal shock, which just causes thermal cracking. So it's not, it could be weather-related thermal cracking. So there's a whole bunch of stuff that needs to, and a lot of the large contractors are doing this. They put in monitoring systems, and there's a lot more of this going on now because these probes you can put in concrete and wireless monitoring systems are pretty economic now for big jobs. It also has information in the annex about insulation. Well, they're to reduce the thermal gradients using insulation. They're talking about 20 millimeter plywood protects concrete because it's insulating, but steel forms just pull the heat away. There's no insulation at all in steel forms, so you get different performance just by the type of formwork that's being used in terms of thermal, minimizing thermal gradients. So in steel forms might require insulation. Okay. Now the other new annex is on ultra high performance concrete, which has been, as I said, has been hitting the industry. And that's not a huge impact at this point, but it's growing. And it discusses how to deal with it because it's a completely different type of concrete. So it provides information on how to what's considered ultra high performance. As I mentioned earlier, there's two minimum strength classes, 120 and 150 MPa. These are tested on even smaller cylinders, 75 by 150 cylinders, because it's so strong that testing in a regular testing machine would be difficult. And you typically keep them in the molds till they're at 100 MPa. Some of these ultra high performance concretes contain fibers, in fact quite a few of them, because a lot of the requirements also include tensile strength and ductility requirements. So it's not just the compressive strength. So we've got three designations here in that annex based, and DL stands for design life. So you have a 50-year design life, 100, 200. Now they're a bit arbitrary, but they've set requirements for things like abrasion loss for like pavements and that, or things like dam spillways, salt scaling requirements, which are much tighter than the MTO's requirements of 0.8 kilograms per square meter. Absorption requirements, chloride permeability require the Coulomb values. You can see they're very low. And sulphate resistance. That's what's in there now. It's an annex. It's not mandatory, but it's an annex. And so it's different than other concrete. It involves particle packing. All the materials, including the cement, the fillers, and the fine aggregate materials are particle packed. The maximum aggregate size is typically masonry sand. Now there are some with up to 8 millimeter aggregate, but typically we're looking at -3 millimeter, that sort of size aggregate. And you're optimizing the packing down to the nanometer level with these ultra-fine powders, silica fume, and even finer fillers. And it requires a lot of heavy mixing to get it to go. And it shows them pouring it out of a bucket there, a wheelbarrow. We need high intensity mixing, high shear mixing, high superplasticizer doses, and a lot of this stuffing. It's very dry to begin with because you're looking at water cement ratios less than 0.2. And so it looks like dry sand almost. And you mix it and mix it and mix it, and eventually after a period of time it starts to flow and it becomes this liquid material like that wheelbarrow there showing in the picture. And it needs to be, it's typically self-leveling, but to get reproducible results, there's a lot of control that has to be exercised. And of course, it's expensive. It's in a whole other ballpark for cost. But it shows them here using it to for the joining panels for precast, some sort of precast deck unit there. Where they put in high-performance deck units, and then the rebars there, and they're putting in the filler strips, they're putting in the ultra-high performance material. And they consider all the fine materials in this, so not just cement and SEMs, but even things like ground powders of various sorts would be considered in this water fines ratio. And it shows the sort of strengths you can get at 7 days steam cured or 28 days water cured, the types of strengths we're talking about. This is an old paper, I just took it as an example of what you can get with these sorts of concretes. So it's a whole different animal. And one example in Ontario where it was used is up near Thunder Bay on an overpass or an underpass. And they used pre-stressed ultra-high performance T-beam pile pier caps. And they made the column forms that are there. That's a column form out of ultra-high performance stay-in-place column forms. They put them in them and they erected them. They put the rebar inside and they put regular high performance concrete on the inside. So the outer part that's exposed to salt is ultra high performance. And then they use filler strips on the precast box units, filling up the pore strips with this ultra high performance material. That's what it looks like. So that's ultra high performance on that, the beam here, a cross beam, and then the stay in place formworks, and then on the filler strips on the deck. Okay. Anyway, of course, in the terms of A23.2, the test methods, we're constantly updating the foreman style to make sure that they have precision statements and the wording is clear. But the only new test method, as I mentioned, is this new bulk resistivity test method, which is 26C. And the reason is, eventually, hopefully, it might replace the A23, the tweak A23.2 23C, the rapid chloride permeability or the Coulomb test. It is much faster. And you can also test whole cylinders with this method. You don't have to cut discs out of it. So you could actually take a cylinder, measure the resistivity end to end, and then put it in a testing machine and break it for strength. But at this point, because it's new, we've put it in there so people get used to it, and so they can look at how it the results compare. But there's no test limits yet. We're going to wait and see on that. So the top test is the 23C. You take a 2-inch disc or 50 millimeter thick disc of a cylinder, you put it between two cells with salt solution or hydroxide solution in, apply a voltage and measure the electric current that flows through the concrete. You measure that over 6 hours, you multiply the current times time, and you get coulombs. And so you get, that's the test people have been using for the last while. And so it's a fairly rapid test, but it takes a day to set it up to vacuum saturate. It takes a day to run the test. It's a 6-hour test. This bulk resistivity test, you apply electrodes on the end of the cylinders, to a whole cylinder, and you measure the electrical current or resistance to electrical current flow, and then you correct it for the area of the cylinder and the length of the cylinder, which is that little equation there. So resistance times the area of the cylinder divided by the length gives you a resistivity value in ohm meters. And you can do this test in 1 minute. If the concrete's wet, you put it between the two electrodes. The test takes a minute. You get a result. You basically get the same information as that test that took a whole day. So it makes it much cheaper. There's at least 3 commercial suppliers. I think there's more, but these are 3. German Instruments has one. And they use a carpenter's clamp to clamp the electrodes in place to get good contact between the electrodes and the cylinder. Archon out of Ottawa uses one where they have 2 electrodes with sponges on the ends, and they clamp the ends down, or you can throw a weight on top. And ProSec has one too, where they, again, the electrodes on top and bottom with some wet sponges. It needs a weight on top to get enough contact. So it's a very simple calculation. It's the resistance you measure multiplied by the area divided by the length. And some of the machines actually have a little computer that does that calculation for you. And just as a rough comparison, we didn't put this table in because people were resistant to suddenly putting limits in for a new test method. So this, but this provides some rough comparisons to Coulomb values that we're used to. So 1,000 coulombs, which would be ultra high performance concrete, will be around 200 ohm meters resistivity. I think MTO's got a 2,000 coulomb limit, which would be the 100 ohm meters resistivity. And so if you do it on the same sort of ranking levels they use in the 23C, those are the sort of ranges you would have. But right now, it's just a rough guide. We want people to do the test. Number of labs are doing the tests, so they do the comparative testing and get comfortable with it. So that's what I'm saying here. It's a simple test. You just have to have a completely saturated sample to get reliable results. If the concrete's not wet, concrete's a good resistor when it's not wet. If it's saturated, then you're measuring the electrical flow through the pores in the paste fraction of the concrete. Okay, so I'm getting at the end here. So the CSA documents are living documents, every 5 years we come out with a new one to fit into the building codes, and people in the committee bring forward issues that the industry is facing. We try and deal with them, or we correct problems that have existed with the current wording. So we're trying to move ahead. But we're, things, the industry changes, the materials change, the practices change, so we're trying to adapt to that. So we're already getting new business for the next edition. We're trying to assemble new business, things we need to address that people are bringing forward. We don't always get it right. We try our best. And so if you have issues you see with the current standard as you use it, feel free to contact CSA or myself and express your concerns of things we might want to address in the next edition, because if we aren't aware of them or nobody's bringing them to our attention, they may not get addressed. Wonderful. So I think that's it. So I think it's question time.
Perfect. We do have some questions here. The first one I can address: will the presentation be available afterwards? Yes, we will be sending a PDF copy to everyone that attended today. Next question: when will this edition be adopted by the Ontario Building Code?
Well, the National Building Code, we had to meet the deadline of July to get in the next edition of the National Code, which I think comes out early next year, 2020. And then the Ontario Building Code Committee meets and usually adopts the changes in the National Building Code, is my understanding of it. Although Rick McGrath from the Cement Association, he serves on all those various committees, so he is better equipped to answer that. But I'm assuming that late next year or early 2021.
Okay. The next question pertains to mass concrete. Whose responsibility is it to specify the maximum allowable temperature for mass concrete? And then the follow-up, as a concrete producer, I'm repeatedly being asked to provide the temperature necessary to mitigate issues.
Well, I would assume that the designer sets the maximum temperature requirements, the specifier. And if the producer may have to do some mock-ups or something to try and see if they meet that, and work with the producer or with the specifier to see if it meets the requirements. I know we've done that, and of course that works on big jobs. We've done insulated 1 cubic meter pours. We put thermocouples in the center and at the corners on the surface, and measure the max temperature and the gradients. But we've done that for like infrastructure projects.
Okay. I had a question about the new slump requirement for floors. Like, typically we leave the slump requirements up to the contractor and the ready mix supplier, but now we're actually going to be specifying a very specific slump for industrial floors, I believe. Can you just elaborate on why that was moved forward with? Well,
was health and safety reasons. I forgot to put a slide in explaining what those were. Apologize. I can't remember what it is. It's the Floor Association was responsible for it, because he says people were speccing these low slumps that were very difficult for them to place and finish. So the idea is to have a minimum slump to allow them to do a proper finish on the floors. And I can't even remember what the number is. I apologize for that.
Okay.
You always find
Looks like that's pretty much it. So thank you very much, Doug. We really appreciate you providing the updates. I'm sure everybody that participated today got a great overview of the new specification. And hopefully everybody buys a copy as well, so we can start implementing CSA 2019 across the province. So again, thank you very much, and safe flight to China.
Yeah, thanks very much. My favorite place to go. Okay, thanks everyone. Thanks for putting up with it.
Thanks, Doug. In terms of publications, I mentioned this previously. We are updating our Power of Concrete publications. We did update the CSA exposure classes, residential concrete requirements, which haven't really changed. Curing concrete, hot weather concreting, proper field testing of ready mix concrete. It's just a summary of the field testing methods. And then we also updated slump, air, and cylinders Those are all ready to go. They're going to be released in the next couple of weeks. We're just waiting for CSA to give us permission to use some of the tables, especially for the CSA exposure classes. We're using tables 1 to 4. So we do need permission before we roll that out. And that's pretty much it from my end as well. Again, thank you very much for tuning in. Our next webinar is being finalized as we speak, and we'll be sending that information next week about the topic and registration details. So again, thank you to Doug. Thank you to everyone for tuning in, and we look forward to your participation next time around again. Thank you.